Hey, D. Dykstra here with another great video on calculus. Today we're talking about the mean value theorem. Alright, so what is this theorem all about? Well, let's look at some quick definitions. Here we go. If f is continuous, so some function is continuous, meaning you can draw it without picking up your pencil. We talked about that in the mean value theorem for differentiation, and now we're going to talk about it with respect to integrals. So, if it's continuous on a closed interval from a to b, then there exists a number c in the closed interval from a to b such that the integral, or the area of f of x dx, is equal to f of c times b minus a. Alright, so what are we trying to say there with that? Well, let's look at a quick little picture. With our Riemann sums practice, what we learned to do was, before we start doing definite integrals, is we know that if we find specific rectangles, we can find a greater amount or a lesser amount. And so some rectangles will be over if they're, say, right-sided or left-sided. And so we call those our inscribed, inside, or circumscribed. So what that means is we've got different varying rectangles, and we learn that if we take certain numbers of rectangles and we were to divide up them under a curve, we would start to approximate the area. And we did upper sums and lower sums, and we said, well, the area is probably somewhere in between. All right, well, here's another way to sort that out, and that is, what is the value of the c that goes right to the curve, right? What if I have a rectangle A from A to C, some value c? Well, what if my f is the blue line, right? So here's our f that's continuous. That's our function. And from A to C, well, this area is above, right? Well, then we go, well, what about from C to B? Well, we find that we want the same height, so this one is circumscribed, and that's inscribed, and that's inside the rectangle. And so we don't get a very good evaluation. But there's got to be a value between A and B, this C value, that hits right here, right on the curve, that if we took enough of those, an infinite amount of rectangles at those levels all the way across, then we could dice this thing up and we would find an exact area. So C is precisely equal to the area. So it's right on the curve. It's got to be a value. Either I'm over the curve here or I'm under the curve. So the rectangle from C to B, this blue one, is less than C, right? And the green one here is over the curve, so that's greater. So C is going to be right in that middle spot. All right. So, and by doing that, what we're going to do is we're going to take, what is the function? We need to find C. The directions will tell us, hey, find what this C value is, and then subtract B from A, and you'll get what the area of that function is. Now, if you recall from our days with differentiation, what we did was we found f prime of c, and we set that equal to f of b minus f of a over b minus a. And so when we did that with the derivatives, we were finding out what the mean value was, or that what was the value of the tangent line that was equal to that secant line. So we drew a secant line, and we said, well, there's got to be some c in between the secant line that gives us the tangent line that is precisely the value of the derivative. All right, so now let's look at an example here of this deal. All right, so let's move this over a little bit here. Follow me. All right, good. Now, example number 1. Use the mean value theorem for integrals to find the value of c. Okay, over the given interval. So here's our function, f of x is x cubed, and we want to know from 0 to 3. All right, so in here we've got 0 to 3. We're looking for a c value or an x value that will give us the y and to construct this area. So we're going to take x to the fourth, right? So we need to find the antiderivative of x cubed. So in order to do that, if you recall, we take 3 plus 1 and we divide by 3 plus 1, right? If you recall that's called the power rule, and it's just the power plus 1 divided by the power plus 1. That gives us x to the fourth over 4. We evaluate it from 0 to 3, and so here I have 3 to the fourth divided by 4, and from the first fundamental theorem of calculus, it's f of b minus f of a, so we have to go through that process, minus 0 to the fourth gives us 81/4. Now, that is the area, right? But now we want to find the c that will be precisely there. So here's our f of c multiplied by our b minus a. In this case, it's 3 minus 0, so that turns into a 3, equals 81/4. So we get f of c. So the function at c. Well, this, we need to just plug c into our function and then solve for c. That's really all we do. That's the basics right there. Don't overthink it, okay? So here we have f of c is equal to 81 divided by 4 divided by 3, because there was that 3 there. So we had 3, and I just simply divided by 3 and divided by 3. Okay, so just so we're not getting lost there with the arithmetic. Then f of c equals 27, because 81 divided by 3 is 27/4. And then now it's f of c. Well, c is the letter we're going to look for is a variable. So here's c cubed. See, all we did was we plugged c into the function. We had a function of x cubed over there, so we just plug it in there. So that's equals 27/4. I need to get c by itself, so I take the cube root of each side, and we get the cube root of 27/4. And there is a perfect cube for 27, that is 3. So c is 3 divided by the cube root of 4. And if you plug that in your calculator, you get c is equal to 1.89 with some rounding. And then you want to check, is that c value, is it within the interval? Well, they gave us an interval of 0 to 3, right there, 0 to 3. Is 1.89 in that interval? Well, yes, it is in that interval, so it checks out. So that value is a good value for c. Anyway, this has been a great time with you today, talking about the mean value theorem for integrals, with a great example and artwork to go. Anyway, hope you've had a great day. Thanks again. And this is D. Dykstra. Peace and love. Thanks.